Very easy, some of it to be a little bit on the tougher side notationally. Let me ask you this before we totally get started. Check out the screen. Do you guys remember seeing this symbol? In a pre-calculus class? What does that symbol mean? Sum. Yeah, so it's a capital sigma, which basically just means add up a bunch of stuff that comes after this symbol. So we'll come back around to that here in a little bit, and I think you'll see the point of that very soon. Okay, so last time what we did is we tried to figure out a way to estimate the area between the x-axis and a curve by using rectangles, right? And in one or two cases, trapezoids, but it was a lot of rectangles. So let's go back to that. So let's say that I was going to, I'll make it easy on myself. Let's say I was going to estimate the area of the curve, and I was going to do something like this, and maybe something like that. What kind of rectangles am I drawing in? Green ones. That's a good start. What else? These are right sum. Yeah, these are right sum rectangles. Maybe the next one would look something like that. Those all making sense? I could draw in these right sum rectangles, and let's say that I was gonna try to figure out this full area between 0 and 8. Goodness, something like that. Maybe I could squeeze one more in. Yeah, something like that. If I was going to, do this, I would have to acknowledge right away that this is definitely an estimate. It's going to be a little bit too low or a little bit too high. It's not going to be the exact area, right? So, question number 1. If I wanted to find not an estimate of the area, but the exact, I use that word, exact area, how many of those rectangles would I really need? Say again? I would need an infinite number of them. Yeah, so infinitely many rectangles. Let's think about what would happen if I tried to do an infinite number of rectangles. And I won't draw all these in, but check this out. So let's say instead of 1, 2, 3, 4, 5, 6, 7, 8, so I got 9 of them up there. Let's say I wanted a lot more. So let's say I did rectangles like this. Can you see how this would not lead me to an infinite number of rectangles, but it would be a lot more? Right now it's trending towards roughly, maybe 3 times as many. You see what I'm doing there? All my red rectangles appear to be about 1/3 of the width of the green rectangles. So if I did have infinitely many rectangles, what would those rectangles look like? Say again? Lines. Yeah, wouldn't they be super skinny? You can see how already my red rectangles are starting to look just like vertical line segments, aren't they? And if I did more and more of them, like infinitely many of them, they'd get closer and closer to just being lines. And can you, just from like a visual perspective, can you see how if all those rectangles were just like lines, like vertical line segments, wouldn't that, if I added all those up, wouldn't I get the area? I'd get the exact area, right? If they were just 1 point wide, just a line. Okay, so if I was going to try to do this, what is the only way that I can really kind of like work with infinity? What concept that you've done many, many times this semester and last semester, what concept would we have to use to deal with infinitely many things? A limit. So at some point you're going to have to do the limit as n approaches infinity, where n is the number of rectangles. Because if you had the number of rectangles heading towards infinity, the width of each rectangle, or the base length, would approach 0, and you'd have those little line segments that Zach was talking about. Does that make sense? Okay. So here's what I want to do. I want to take you through a little exercise. We'll get to a good place. We'll do 2 more examples kind of together. It's going to, symbolically, this is going to look a little intimidating at first, but I have a way of doing this that I think will make it a little bit easier. I'll show you. Hopefully you'll agree. We'll just see. So I'm about to show you kind of a development of this. We'll arrive at a good place, and I'll kind of tell you what I would expect you to do with this. So let's just pretend that we were supposed to find the exact area between 0 and 8. So basically the area that I have outlined up there. That makes sense? Okay. So let's think about what this could look like. I'm going to put area is approximately. We're going to start off with an approximate area. If I was going to divide this interval from 0 to 8 up into a certain number of subintervals, let's just do it for example. Let's say, like this was back last week, and I said, let's use 4 subintervals. How wide would each subinterval be? How'd you get that?
8 divided by 4.
Yeah, 8 divided by 4. Now, I'm leading you somewhere, so don't be like, well, why are you asking me about arithmetic? We're going somewhere. Well, let's say that I said, you know what, let's take this same 0 to 8, and let's divide it into 8 subintervals. How wide would each one of them be? How'd you get that? 8 divided by 8. What if I wanted flexibility? What if I didn't want 4 subintervals? What if I didn't want 8 subintervals? What if I wanted n subintervals? So I could make the n whatever I want. How wide would each subinterval be if I divided that 0 to 8, not into 4 subintervals or into 8, but into n? Wouldn't it be 8 divided by n? Just like you did 8 divided by 4, or 8 divided by 8, it'd be 8 divided by n. So what I'm going to do here is this. I'm going to look at this first rectangle, and I will sort of color, I'll just make little marks on it. This first rectangle, let's think about the area. Wouldn't the area be the base, which you all just said was 8 over n, or at least some of you said? Wouldn't that base length be 8 over n? And I'll highlight that in blue, or I'll color that in blue. And then, how do we know the height of that rectangle?
The y value
Of the curve, right? Yeah, over on that right side?
Yeah.
Totally agree. It's the y value of the curve on the right side. So I didn't give you a function for this. Let's just call this, just for sake of notation, let's just call this f of x. Okay, so we're going to use the right side x value to determine the height. Would you guys agree with me that that height would be f of 8 over n? I don't have any idea what 8 over n is because I don't know what n is. But I know that whatever that point is, if I just plugged it in, I'd have the height. Is that making sense? Carson.
Wait, why is it 8 over n? Couldn't it just be 8?
Well, so the area formula for a rectangle is base times height. And that 8 over n is my base. And so the full interval here is 8, no doubt. But for this first little rectangle, the base length is not 8. For that first rectangle that I've kind of highlighted right there, the base length is 8 divided by however many subintervals I used.
Oh, it was the first rectangle. I thought you meant like at the far right side of it.
No, just the right side of the first little subinterval. That make sense? Okay. So then, obviously, there are plenty more of these rectangles. So here's another one. So one's going to be very similar but different. So I'll put plus. What is the base length or the width of that rectangle? Talking about this little bright red length. What do y'all think? How wide was the first rectangle? How wide do you think the second rectangle will be? Wouldn't they all be 8 over n base? Like all of them have a base of 8 over n. So I'll put 8 over n plus f of, and this is where it gets a little bit different. Yeah, there we go. So just like before, the height is going to be based on the y value of the curve. And Jed just said it. I'll just put it in here. It's f of 2 times 8 over n. Now, why would it be 2 times 8 over n? Let's think that through. I'm going to highlight this in red. Isn't this just an x value? Isn't this just some other x value? So, probably should have used wider rectangles, but it'll be okay. From here to here was 8 over n, wasn't it? So then from here to here, wouldn't it just be 2 of them? What would you guess the next one's going to be? 3 of them, right? Yes, exactly. We'll get there in a second. Yeah.
Are those 2 terms in the red supposed to be multiplied?
Oh, darn it. Yes, they are. Let me fix that. Thank you for asking. Yeah. Because the area of a rectangle is not base plus height, is it? So 8 over n times f of 2 times 8 over n. Okay, I'll do one more of these and we'll try to sum these up. So here's the third one. It's purple. And hopefully you're starting to see the pattern. What's the base length on the purple rectangle? They're all 8 over n width, aren't they? Like if you just look at each base, they're all 8 over n. And then the height, again, would be the y value of the curve. And wouldn't that be f of 3 times 8 over n? You guys all following okay? Okay, I'm going to do one more notation here. I'm going to say plus dot 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 plus my final rectangle, and who knows how far it is out there, but it's out there somewhere, would be 8 over n still times f of what times 8 over n? What would you guess? Say again?
Infinity.
No. How many rectangles do I need? I need n of them, so the last one would be the nth one, so it would be n times 8 over n. Okay, what's in common amongst all of these terms? They all have an 8 over n factor. So my next step then would be to factor that out. So I'd say area is approximately 8 over n times the quantity of f of 8 over n plus f of 2 times 8 over n plus f of 3 times 8 over n plus dot 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 plus f of n times 8 over n. There we go. Okay, so can you all see that what I'm highlighting here in green is basically just one long summation? So this might be where there's kind of a big leap. I'm going to say that this equals the following. Sigma from I equals 1 to n, because again I want to go from either one rectangle, because I need at least one, go from one rectangle all the way up to n, whatever that number might be. And here's what's inside. Here's what I'm going to be summing up. 8 over n times f of 8 over n times I. So that I, based on the sigma, is going to go from 1 to 2 to 3 to 4, dot, 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 all the way up to n, right? So I'm basically taking that long list of addition and saying I could write this way easier by just going sigma of I equals, from I equals 1 to n, of that f of 8 over n times I. Just a word of encouragement here. Like, all of this development stuff, really, to be honest with you, is nothing that I'm going to expect you to do on a repeated basis. I just want you to see where this comes from. Okay, so then last big chunk here is this. The formula that we have written down here in this lovely reddish box, that is the formula for the area under the curve for n rectangles, n of them. So if I said, you know what, I want to use 1,000 rectangles, I would just replace the n with 1,000, probably use my calculator, and I'd be done, right? If I wanted to use 1,000,000 rectangles, I would just make n 1,000,000, do a bunch of adding, preferably with a calculator, and I'd be done. But what did we say in question 2 and 1? How many rectangles would we need to get the exact area? And what's the only way to deal with that? A limit, right? So we need infinite number of rectangles. We have to use a limit to do so. Here's how I would wrap this up. I'm going to try to write this in the little space there at the bottom. I will say, here's our final area. Now I'm going to write area, not approximately, area equals significant difference, right? I'm going to say this is the limit as n approaches infinity of sigma from I equals 1 to n of 8 over n times f of 8 over n times I. What's significant about that is I've gone from an approximation that we for sure know will have errors to an exact value for area by saying, hey, we want the number of rectangles to approach infinity. This would result in the exact area under the curve. What do y'all think? Let me highlight really what the end goal is, what I would hope and expect that you would write. It's right here. I want you to be able to get there. And honestly, I want you to be able to get there without doing all that junk in between. Okay? I really, really don't want you to have to write down all that stuff in between to get there. And that's what I want to show you here in our last couple of minutes. You okay with that? Okay. Do you see why people get intimidated by this symbolically? I think there's sigmas and there's i's, and oh my gosh, now there's a limit, and infinity is always hard to think about. So let me show you what I would want you to do. Check this out. There we go. Oh, and by the way, that last little thing that I wrote is called a Riemann sum. Sorry, I didn't say that. Riemann is named after this old mathematician who is pretty famous in the world of math, GFBW Riemann. Have you ever heard of Riemann's last theorem? It's one of those theorems that has yet to be proved or disproved. You can earn it might still be $1 million if you can prove or disprove it. People have tried for hundreds of years. It's called his prime number theorem. Anyways, so same Riemann. So here's what we would do. Take a look at number 1. Number 1 says, write a Riemann sum expression, which is what we just did there at the end, for the area under f of x equals x cubed on the interval from 2 to 5. Now, if you wanted to draw a graph and draw the rectangles and do all that development, you could, but here's what I would suggest you do. If you see this term, write a Riemann sum expression, then I would suggest you go in this order. Start with the easiest stuff. Okay, so check this out. The easiest stuff is, you know that a Riemann sum will always be the limit as n approaches infinity of sigma from I equals 1 to n. So start off with the easy stuff, for goodness sake. If it asks for a Riemann sum expression, every one of them is going to have that. So don't start anywhere else. Just start there. And then remember, and I'm going to erase this, so you can write this if you want. I'll erase this, so maybe you don't write it. Remember, isn't it just basically the infinite summation of base times height? It's area of a rectangle plus area of a rectangle plus area of a rectangle. So with that in mind, I think the next easiest thing to write is the base length. So the interval here is from 2 to 5. So what would you guys guess the base length would be for each one of those little rectangles? 3, so whoever said that, 3 over n, right? Because how far is it from 2 to 5? 3. And how many little subintervals do we want to use? N of them. And so I would say that my base length is 3 over n. So it's easy. The easiest place to start is, you know, it's going to be a limit of a sigma. The next easiest thing is to recognize the base length will just be interval width divided by n. And then the height is the toughest. There's a couple of little things in here to think about. So I'm going to go times. Now, isn't the height based on the y value of the curve? And isn't the y value of the curve essentially input cubed? Right? F of x equals x cubed. So I'm just going to say my height is input cubed. Making sense? And the input is probably the toughest of the things to deal with. So here's how we deal with the input. On my interval, what is the lowest possible input? 2. Don't we start from 2 and go to 5? My lowest possible input is 2. Now, on the example we did earlier, this might be what you're thinking about, wasn't the lowest possible input 0? Because we started right there at the origin. So right now we didn't start at the origin, we started at 2. So the lowest possible input was 2. But then I've got to move across the page. And every time I go from one rectangle to the next, to the next, to the next, how much am I adding on? Say again? Not n. Isn't it each rectangle is a width of 3 over n? So every time I add 3 over n, plus 3 over n more, plus another 3 over n. So I would say it would be 2 plus 3 over n times I. Remember that little I, the little element of summation? And that would get me my Riemann sum expression for this area under the curve. I thought I could get 2 examples in. We'll try to do the second one tomorrow. So have a wonderful day, you guys. I will see you tomorrow. Carson, your question.
Would we get it wrong if we just put like the function f instead of actually doing the...
You want to be specific. I'm thinking of like multiple choice, but I would say like if f is clearly defined,
Then we would want to plug it in.
I don't know that it would save you any time, but if f is clearly defined, I think you're good. I think either way would be
I
fine.
signed up late and I was the only one left. It was like 30
I'm just thinking about the way that like multiple choices are usually formulated. They're usually not like that, but
Like the business.
you would not be wrong at all.